All right, this is Mr. McMurray. We're in Chapter 29, Geologic Time Notes. And just for the record, I was not alive during these actual times, so I'm not an eyewitness of these things. These are things that how can we determine how old things are and so forth, and how much certainty can we put in those dates and stuff that we hear people talk about, how old certain fossils are and things like that. And we're going to talk a little bit about that. How can we put things in order in geologic time? All right, and the first thing we're going to talk about is relative dating. Okay, this is not dating cousins. That might be okay in Alabama and a few other places, Arkansas, whatever. But we're not talking about dating your relatives. Okay, we're talking about dating layers of rocks relative to each other. In other words, which rock layers are older and which ones are younger. Now, we're not giving an exact age. Okay. All right, but we're just saying relative to each other, which ones are newer, which ones are older, and that sort of thing. And so these are just some general rules that we can use to say which rocks are older than others. All right. First principle of relative dating that we're going to talk about is original horizontality. Horizontality. That's a big long word. Basically, it just means that when rock layers are laid down, when sediments are deposited, okay, they're going to be deposited in these flat layers. If we see layers that are tilted like this, we can be pretty sure that when these sediments landed here, it was not tilted like that. Okay, so what we're saying is that layers are originally deposited. When new stuff comes down and makes new layers, it makes flat layers. Now later they may be caused by earthquakes and volcanic activity and upthrust and various things, uplifting of the earth. It may be tilted like this, or it may be folded so they go like this. But when they originally landed, when the sediments were originally deposited, they were originally in horizontal beds. All right. So if we see them tilted or folded, we know the tilting or the folding had to happen after the actual layers had been deposited, and therefore they happened after they were deposited. All right. So that gives us an idea that whether the fault happened before or after these particular sediments were deposited. All right. The second rule is going to be called superposition of layers or of strata. Okay, and by strata just means layers, or stratus clouds, which are just thin layered clouds. Okay, but it just means layers. So superposition, in other words, if this layer is on top of this one, which one happened first? Well, this one had to be deposited first, and then this one had to be deposited after it. Or for that matter, if we go down here, if this one had to be first, then this one second, then this one third, this one fourth, and this one fifth. Okay, the closer it is to the top, or the higher it is, superposition, overposition, means that it is younger. The lower position means that it is a younger layer. Okay, and that just, if it hasn't been disturbed, hasn't been tilted, hadn't been folded or whatever, if we have flat layers, we just have to assume that the lowest one is the oldest, and the highest one near the surface is the youngest. All right, principle number 3 is known as cross-cutting. Okay, if we have something that cuts through layers, okay, for example, a fault, if it were to slice through these layers and some of them were scooted up and some were farther, we know that since it cuts through these layers, it has to be more recent than those. Okay, otherwise it would not show up. Okay, also, if there's anything that cuts through it, like a dike, which is when igneous rock comes up through a crack, if it cuts through these layers, we know that this dike had to have happened after these layers were set down. All right, actually we have 3 different dikes where magma underneath the ground has come up, and because of this, we can say that C is the oldest of those. C happened after all these were laid down because it cuts through them. B cuts through C, so we know that B had to happen after C, and A cuts through dike B, so we know that it had to be the newest or most recent one. Okay, and so this is the principle of cross-cutting. If something cuts through the layers, it has to be younger than those layers themselves. All right, number 4 has to do with inclusions. Okay, inclusions are things like this where there are pieces of rock that's embedded in these sediments. Okay, big chunks of rocks. Okay, now in order for these pieces of rock to be contained in these sediments, that means they have to be older. Okay, the inclusions have to be older than the layer that you find them in. For example, if we go out and find concrete with gravel in it, or rocks, little pebbles and rocks that they put in it, we know that the rocks had to be put down with the concrete. So you already had the rocks before you made concrete. It's not like you poured the concrete and all of a sudden these rocks formed in the middle of it. Well, the same thing here. These layers didn't form and then all of a sudden these rocks just poofed up or somehow showed up in the middle of that layer. They had to have already been around, okay, when this other stuff was being done. So we know that these inclusions here, these little pieces of rock formations or rock that are up here in these sediments, must have been formed first before the sediments were deposited. Now, the first four rules apply to things that are found nearby each other, and they're pretty much, you can see how those would work. Okay, now the next couple are a little less specific, but they're still important. And number 5 is lateral continuity. All right, lateral means side to side or all around us. So lateral continuity. When these sheets were being laid down, they weren't just being laid down in one spot. For example, if there was a layer being laid down here on the Grand Canyon, it was not only being laid over here, but we'd expect out here on a little mesa or butte the same size, we'd expect to find those same layers out there. On the other side of the Grand Canyon, we might find the same type of formation. Okay, so there's lateral continuity. That means these sedimentary layers were deposited in all directions in a large area, unless there was something that stopped them from doing that. Okay, for example, if they're being laid down in an ocean bed, well, once you got to the beach, there might not be any sediments being laid down on the beach, but there was as far as the ocean stretched out into the ocean. But so basically, that they're all areas of this large area. Okay, now the problem with this is over time things could happen. Some layers can be shoved up, okay, and so it may be hard to tell which ones match the ones that are found somewhere else. Okay, you could have faulting where some either slide down or slide up. You could have different kind of erosion that happened in some areas but not in others. Obviously in the Grand Canyon area, the erosion was not equal in all places and all areas, and so you end up with a big canyon going down the middle of it. All right, and if you look at one side of the Grand Canyon, for example, compared to another, you might have a little more trouble lining these up. Okay, if it's continuous like a big piece of ground, then yes, they're probably going to stay pretty continuous. But for example, here we have shale here and we have shale here. We have shale here and we have shale here. Where do these match up? Well, it would help if we knew what was down here. So if we found there's limestone down here, then that would probably correlate here. This shale would be that, and this sandstone here would be this sandstone here. Okay, and then this stuff would be newer sediments that no longer show up here. And at some time, this has been lifted up, or this one has faulted and fallen down, if that is the case. Okay, now, the bigger the distance between them, the harder it is to correlate them. Okay, but we can still kind of see and try to match up which ones go together. But keep in mind, this sometimes is less than an exact science. Okay, we use the best information we have, and the more information we find, the better we're able to match them up. All right. All right. Now, the last thing is faunal succession. This is a way we use to help correlate some of these far apart layers and try to figure out which ones match with where. As engineers were digging in the earth and doing different projects to dig, some of them started to notice there's a famous one called Strata Smith. His nickname was Strata, not his real name, just for the record. His parents weren't quite that crazy. But at any rate, Strata Smith, because he would look at the different fossils that he would find, and he noticed that even if he went in different places fairly far away, he would find fossils of organisms in about the same order and the same pattern in all the different rock layers. And so basically, what he said is that faunal succession is that fossils or fossil organisms follow each other in a definite, irreversible pattern in time. And so, for example, if we found let's just say a trilobite, which is a little horseshoe crab looking thing right here with a little tail coming out. If we saw them in this layer, and we also saw them in this layer, then that would be a correlation that these two layers probably match. We might find other fossils, let's just say some type of certain kind of clam, okay, and a certain type of clam over here, and then we could correlate those layers and say yes, because these seem to, in all the different rock layers we found, we've always found these before those, so we would expect that these two match up. Okay, now this is best useful for fossils that didn't live for a long time. I mean, if there's things that have been around, like for example, certain kind of clams may have been around for forever, right, basically, okay, one form or another, and so it's hard to use them to figure out how old the fossil. Other things like trilobites that aren't around anymore and have gone extinct somewhere along the way are more useful as an index fossil. An index meaning that gives us an idea about when that rock layer may have formed. Okay, sharks, for example, have been around for so long that sharks' teeth, which is about all that's left of them because their body's made of cartilage, may not be a real useful indicator because they've been around forever. It could be any age. Now, you have to be careful because after a while, if you're not sure, you say, well, we know how old this rock layer is because it has these fossils in it. And then someone says, well, how do you know that these fossils match up? It's because, well, they're the same age. Well, you got to be careful. You use circular. We know it's this old because of the fossils in it, and we know it should have these fossils in it because it's this old. Okay, if you're not careful, you can get a little confused there, and it may be off the mark sometimes. But in general, there are certain index fossils that live in certain time periods, and so if we find them in the rock layers, we can assume that that rock is about that age. Okay, we'll talk more about how we actually date rock layers in a moment. All right. Now, sometimes on science shows or talking about it, you kind of get the impression that we can see a complete, exact copy of everything that's ever happened, and we have a perfect sequence of layers going back to, however many, back to the Precambrian or whatever, back when first life began, they think, and all this. And that's probably not, that's overselling a little. There are gaps in the rock layer. If a certain area of rocks was always having layers deposited on top of it, then we would have a complete picture. But where oceans have changed over time. For example, most of Texas, we think at one time, shows evidence of limestone and other ocean-type rocks that would be deposited at the bottom of the ocean. So we think they were underwater oceans. And as long as they're underwater, there probably were nice, steady layers being deposited. But if they get lifted up, or if the water recedes for whatever reason, now erosion is going to start eating away at these layers. Okay? And so let's just say that erosion comes away and wipes off some of these layers. Okay? But over time, it gets underwater again, and they start putting layers again. Well, are these layers just a little bit older than these? No, there's this big old gap here where layers are being eroded away. Okay? And these gaps in the fossil record, that's kind of what we're going to say here, gaps in the fossil record and the strata rock record, I'm sorry, I should say rock record, actually. There may or may not be fossils in all these rocks. Okay, gaps in the rock record, how do we account for that? What are they called? Well, first of all, they're called unconformities. Okay, they don't conform to what actually happened. There's something that's not right here. So it's called an unconformity. Okay, these are unconformities. All right, and this is where either weathering, like this, where layers have been eroded away and then new layers got stacked on top of it. It could be where there's a fault, so some got shoved, like these got tilted sideways, okay? And so now then they have to be eroded back flat before things can be deposited on top of them, okay? It could be that there's faulting and one side gets uplifted, one side gets dropped, okay? All these kind of things we have to try to these interrupt the deposition so that we don't have a regular record of things being deposited here, and so we have to account for that. And so next time we will talk just a little bit more about some of these unconformities and then also about how we date our rocks.